We are going to derive the heat equation from scratch. So, what we're looking at here is just a generic picture of heat transfer going from left to right across the screen. There's a big giant flow domain in question. The little teeny tiny cube in the middle is what is referred to as a representative elementary volume. One of the ways we solve problems is to take a problem on a big scale, chop it up into little teeny tiny pieces, solve the problem on the tiny piece, and then extrapolate that information back up to the big level of the problem. You have done this before. When you first learned how to do partitioning into Riemann sums for a definite integral, you took a big area, you chopped it up into little teeny tiny rectangles, you found the area of each of those, and you added the results back up. We're going to do something similar here. A simplifying factor in this case is that we're only going to design the one-dimensional heat equation, meaning heat is going to be a function of x and t, one-dimensional physically, so that there's less stuff to write down, basically. I'll show you the implication of that in a minute. So to start the problem off, what we do is we zoom in from our big flow domain down to the representative elementary volume. So we're going to watch flow going in and out of this cube. On the left face, we have a coordinate x, y, z marking that lower corner, and the edges are, of course, delta x, delta y, delta z. Because we're only allowing one dimension physically in this problem, we're only looking for a heat flow as a function of x and t, we assume that any flow at this marker on that left face is the same as it is here and here and here. So all we need to know about flow at that left face is the flow at the x coordinate of this point, and that flow is the same all over that face. And then the same thing on the exit side, which would of course have the x coordinate x plus delta x. So the medium that the heat is flowing through is going to have properties. First of all, we are after the function that describes heat or temperature as a function of x and t. We're going to be measuring flux, which is the amount of flow that goes across each face. Now this flux is called volumetric flux. Its units would be something like cubic meters per square meter per second. In other words, there's a big blob of heat, but we'll call it that, a big blob of heat moving across this face. So there's so many cubic feet going across per unit or per square meter of this face per second. So cubic meters per square meter per second. You're measuring the flux across this face. The medium has specific heat, which you may remember from physics, let's make sure I get this right, is the amount of heat it takes to raise a unit mass by a unit temperature, right? The cube itself will have a certain mass, and we have density, and we have conductivity, which will be a constant called K, which is the constant of proportionality from Fourier's law of heat, and it is a measure of the ease with which the medium can transmit the heat or the changing temperatures. So when we set this problem up, we can measure the total change in heat in that representative elementary volume in two different ways. Since we can measure the same quantity in two ways, those two measures have to end up being equal to each other, and that is what drives this entire derivation. So remember that we're talking about the teeny tiny little cube, and we're asking per a unit time how much heat will have gone in versus out. Now based on just the physical properties of the medium, we can get that calculation here. Now that's a whole lot of stuff, so let's make sure that we can track things properly. Okay, first of all, this right here is the volume of that representative elementary volume. If we multiply the volume by the density of the medium, now we have the mass that's contained in that representative elementary volume. And then when we take the mass and multiply it by the specific heat, the specific heat tells us the amount of heat per unit mass per degree in temperature, per change in temperature that we initiate. This is the change in temperature. U represents temperature, so du dt is the change in temperature in a given amount of time. So the specific heat times the mass times the change in temperature tells how much heat is released or absorbed in that representative elementary volume per unit time. Keep that in mind. Let's take a second measure of the amount of heat that goes in and out. This is just simply based on watching the flow in and out of the cube, and we do that with the flux. The flux across this face on the left, if the flux at the left is equal to the flux on the right, there is no net change in heat. We're in steady state. If the flow in versus the flow out is different, then there is a net change in the amount of heat in the cube. If the flow in is bigger than the flow out, more heat's going in than leaving, the temperature is going to go up. If the flow out is bigger than the flow in, there's more heat leaving than coming in, the temperature is going to go down. So when those two values are the same, flow in, flow out, no change. When they're different, there is a net change in heat. Okay? And because we have a quantity that describes that flux, and remember, the x-coordinate is the only coordinate which gets a change in flux from one place to the other, the flux at x times the total area of that face, which is delta y delta z, gives us the total amount of heat going in. And then the net flux at x plus delta x times the area of that face, which again is delta y delta z. That's how much flux is leaving, how much heat is leaving. And so the difference between those two is our second measure of the amount of heat, the change in the amount of heat in that representative elementary volume. So now we have two measures of that same thing, and they have to be the same. So here we've got that second measure set equal to what we had from the first measure, right there. And now we're going to start simplifying. You might notice there is a delta y delta z on every term, both on the left side and on the right side. So why don't we just, delta y delta z. Why don't we just cancel that out? Those are supposed to be delta z's, like so. The net result here is that v of xt minus v x plus delta xt equals sigma delta du dt. All right. Here we're going to kick in Fourier's law of heat, because remember, ultimately, we want this differential equation written in terms of u. U is on the right-hand side already, but it's not on the left-hand side. However, we have Fourier's law of heat, which tells us that flux is proportional to the rate of change, or the gradient, of the temperature function. K is that constant of proportionality. That is the conductivity. So we can replace each of these flux terms on the left-hand side with Fourier's law of heat to introduce du dx. We are also going to say that the K from the Fourier's law of heat divided by sigma delta, that's just a bundle of three constants, and so we're just going to plop that together into one big capital K. Sorry, my screen just went blank because I haven't touched it in long enough. There we go. So imagine I divide sigma delta to the left-hand side and I introduce Fourier's law of heat. I can do the renaming of those constants, and the net result is that negative, now big K. I'm also going to switch to subscripts. There's a change in sign because Fourier's law of heat poses that flux is negative K du dx. So I've changed my left-hand side. This still has to be equal to that right-hand side, except without the sigma delta because I've divided that. Instead of having a negative term added to a positive term, I'm going to flip those around. So we've got K, derivative of u with respect to x at x plus delta xt minus ux at xt equals delta x times u sub t at xt. And now I'm going to move that delta x to the left-hand side by dividing both sides of this equation. And I will have K times this expression. You should be getting quite uncomfortable with that at the moment, because you might know what's about to come next. Remember your difference quotients? Here is a function. Now it happens to already be a derivative, but that's fine. It's a function evaluated at x plus delta x minus that function evaluated at x divided by delta x. Boy, that looks an awful lot like the definition of a derivative, right? And that's how we're going to use it, because flashback. In the calculus 1 case, calculating area under the curve, you take the big problem, you chop it up into a bunch of small problems, you get the area of one of these standing rectangles that was the approximation over this small piece, and then you say, well, if chopping this region up into 10 rectangles was great, imagine what 100 would do, imagine what 1,000 would do, imagine what 1,000,000 would do. We let the number of partitions go to infinity. Here we have a giant flow domain. We've selected a little teeny tiny representative elementary volume, and we've solved the balancing of flow from inside one face out the other face on that little square. That's an estimate of what's going on at any point in space. But wouldn't it be great if we could shrink that representative elementary volume in size all the way down to 0? And in fact, that's what we're going to do. We're going to let delta x go to 0. How do we let delta x go to 0? Limits. And so now we're going to take the expression we currently have. We are going to do a limit as delta x goes to 0. Now that limit has no effect on the right-hand side, but if we take the limit of the left-hand side, we have to take the limit of the right-hand side. This right here is the definition of the derivative of u sub x with respect to x. What is the derivative of u sub x with respect to x? It is the second derivative of u with respect to x. And now we have k u sub x, x equals u sub t. Boom. One-dimensional heat equation from first principles, right? Now you could go back and recreate this for 2 dimensions and end up with k times u sub xx plus u sub yy equals u sub t. You could even throw in a 3rd dimension. We can add a source term. For example, there's something generating heat inside this flow domain. So the balance in a representative elementary volume is not just due to what's going in versus what's coming out, but the difference in inflow versus outflow, as well as what's being generated by a source that's in the flow domain itself. In that case, your heat equation might end up looking something like this, where that is a source term. And then solving these things becomes so much more fun. So there you go. 15 minutes exactly, heat equation in one dimension.